Today's lecture is on cyclohexanes and chair conformations. When we first start out with cyclohexane, we have a planar looking drawing, but it does not accurately represent the three-dimensional structure of cyclohexane. What is better to use to represent the true structure of cyclohexane are called chair conformations. These are the most stable conformations for a cyclohexane molecule. And usually for a given cyclohexane structure, there can be multiple chairs to consider, with one being the most stable, but others having some other stabilities associated with them. And so, for example, for a cyclohexane, I'm going to draw two different structures. I'm going to highlight the axial and equatorial positions. The axial positions are the ones that go vertically straight up and straight down from the carbons that they're bonded to. Each carbon of cyclohexane has two hydrogens bonded to it. One will be in an axial position and the other will be in an equatorial position. From this first carbon right here, which represents a tip angled upward, there will be an axial hydrogen that is straight up from that tip carbon. The way hydrogens work on a cyclohexane is one will be going in an upward direction. On the adjacent carbon, it will be going downward. And then upward, and so on. As we go around the ring. So again, these are the axial positions, highlighted in red. The other positions are usually a little bit harder to draw, but they're easy to draw if you reference them to the axial positions. If there's an axial going straight upward, the equatorial will be angled slightly downward from that same carbon, like such. And this gives you a true tetrahedron around that carbon. So those angles should be 109.5 degrees. If the axial position is going straight downward, the equatorial will be angled slightly upward from that carbon. And so we can fill in the positions going all the way around the ring. Now, if you look at the blue equatorial positions, starting up here, we're going downward. On the adjacent carbon, it's angled upwards, then downwards, upwards, downwards. When I use those terms, I'm talking about upwards or downwards from the carbon that they're bonded to, and that's where you'll focus. And so all of these positions would be hydrogens in cyclohexane. Now with a cyclohexane, all of the carbons can essentially switch in what's called a chair flip. And there's an equilibrium whereby the chairs can go back and forth. And so when there is a flip that occurs, one end will come up and the other end angles downward. And that's the flipping of the chair. The consequence of that flipping is that every axial position will become an equatorial position. And so, for example, down here, this end that was pointed downward that now becomes pointed upwards, the axial position angled straight down will now be angled only slightly downward from that carbon, but still in the general downward direction. The equatorial position that was angled slightly upward will now be axial. on that carbon. And the trend will continue for the rest of these positions, and I'll go ahead and fill them in. Notice how I usually draw my axials first because they're easier, and then when I have the axials, I reference the equatorials to those axials. And these are all drawn very much correctly. When we look at the next example, here we have a substituent, just a bromine bonded to that cyclohexane. So there's two different possibilities for where that bromine could go. And I'm going to draw in those two chairs. You can pause it and try and draw them yourself. These will be my two scaffolds. All of these carbons are identical in the way it's drawn now. So I could put that bromine on any carbon. I just have to choose an axial or equatorial position. I've chosen to place that in an axial position. And of course there's a hydrogen bonded in the equatorial position there, but I'm not going to draw in any of the hydrogens. The only thing that's important is the largest group, the bromine. When we do the chair flip, the bromine is now in an equatorial position. And perhaps you had to draw in the equatorial and the axial position at that site, and maybe you drew in the hydrogen there, just to help as a reference for drawing the positions correctly. Now, here we have an axial bromine, and here we have an equatorial bromine. Which one's more stable? Well, a larger atom or group will always prefer to be equatorial or oriented away from the body of the cyclohexane. The reason for that are 1,3 diaxial interactions. One-three diaxial interactions cause steric interactions or steric hindrance or crowding or bumping into each other. And they only are present for axial positions. And every axial position has to deal with them. And so if we focus on the axial positions in this structure, we can see that in these three axial positions, all oriented directly upward, they're actually pretty close to each other in three-dimensional space if you were to build a model. And so any groups that are of any significant size here will bump into the other axial positions, even if they're hydrogens. The same goes for the axial positions oriented downwards. It's the same case. And so certainly bromine will prefer to be in the equatorial position. And so this chair form is more stable than this chair form. They can still convert back and forth, but this one will be a higher population at any given temperature. Next, we'd like to consider more than one group on a cyclohexane. Now I've drawn in dashes to indicate that the fluorine and the bromine are both specifically going away from us relative to the body of the cyclohexane. And so they're both generally oriented in the same direction. What this relationship is called is a cis relationship. Now this specifies some things when it comes to drawing a chair conformation. So we can go ahead and draw two different chair conformations for this structure. first one, we have fluorine going in one direction. Since it looks like it's going backwards, that would be equivalent to going downwards in the molecule. I'm going to orient it downwards from this position here at the top. That would be an equatorial position. Again, you might have to draw in the axial position to help draw that equatorial. If we number our carbons, and we can start perhaps down here due to nomenclature rules and starting alphabetically, but we would have carbon number 1, 2, 3, and 4. So we can see they're on opposite sides. And so if we have this as carbon number 4 right here, we could have carbon number 3, 2, and 1 down here. So the bromine is bonded to carbon number 1. And so what's important now is that we've defined this fluorine as going downward from the carbon it's bonded to. So because these two are cis to one another and they're both oriented in the same general direction, this bromine must be going downward from the carbon it's bonded to as well. And we'll have to investigate that exact position to know if that's going to be axial or equatorial. In this case, the downward position is the axial position. And so bromine is bonded here. What we can tell from this chair conformation is that we have an equatorial fluorine and an axial bromine. In the opposite chair, both of those will switch positions. And so what we'll have is an equatorial bromine and an axial fluorine. Now, from the energies of these groups and the energy that it takes to put them into an axial position, fluorine being so small, it's more difficult for a bromine to be in an axial position than for a fluorine. And so the more stable form will be when bromine, the bigger group, is equatorial. Now, the best case situation would be if both larger groups are equatorial. That's simply not possible given this specific cis relationship. It can't happen. Well, when can it happen? It can happen in the trans isomer. So when these groups are trans to one another, if you draw in the chair conformation, you'll see that they indeed can be both equatorial or conversely both axial. This is what the chair conformation would look like for this particular disubstituted cyclohexane. Fluorine is oriented from the carbon it's bonded to in a general downward direction, whereas bromine, oriented from the carbon it's bonded to, is angled upwards. And so they're trans to one another. One is going one general direction, the other is coming the opposite direction. You could draw the other chair conformation where these were both axial, and they would still be trans to one another. Now we're going to look at a trisubstituted cyclohexane. And so we have a methyl group, a fluoro group, and an alcohol group, or a hydroxy group. On this molecule, the first thing you have to figure out is what positions are those groups in? Well, the methyl group is axial, the fluoro is equatorial, and the hydroxy is axial, the way I have represented the molecule. First thing I want to do is draw the opposite chair. So try and do that. Draw the result of a chair flip. This should be the result you get. Notice everything that was angled either straight upward or slightly upward is still in an upward direction. And everything that was downward, or just the hydroxy group, is still angled downward. However, everything that was axial in this structure is now equatorial. Everything that was equatorial, or just the fluorine, is now axial. And so we have two different conformations. We need to decide which one's better. Well, usually you can go by the energies associated with each independent group. And so a methyl group is by far the biggest out of these three groups. And the value is roughly 7.3 kilojoules per mole of a preference for the equatorial position. A hydroxy group is 3.9 kilojoules per mole, preference for equatorial. And then fluoro is just about 1 kilojoule per mole. And so this being in an axial position, although not ideal, is okay because the other two larger groups are in equatorial positions. So this chair will be more stable than this chair. Next, what we want to do is so we ran out of power there and we're back on. When considering these two structures, again, we've drawn two different chair forms of the same exact molecule. It's got three different substituents on it. We've seen that this one would be the more stable form. What we want to do now is draw a planar cyclohexane representation with the correct assignment of three-dimensional geometry, so dashes and wedges. What we're actually going to draw is the correct stereoisomer for this exact orientation. So we start off with a planar cyclohexane. Where exactly you put the first group doesn't matter because all these carbons are the same. I'm just going to choose to define this carbon right here as the one that bears the methyl group. And so if we look at this methyl group, that methyl group is going upwards, and to me that's equivalent to coming out at us, upwards or out. And so when I define this methyl group as coming out at us, now I can reference the rest of the groups to that position. Well, the methyl group is going straight upwards. The fluoro that's bonded to the carbon next to it is not going straight upwards, but it's going slightly upwards, still in an upwards direction. And since they're both going upwards, we represent that with a wedge as well. Now when you look two more carbons down the line, opposite from the methyl group, the hydroxy group is going directly downwards. So that would be a trans relationship to the methyl group or to the fluorine. And so we represent that with a dash. Now if we've done this correctly, this drawing should also represent what is observed here. And it certainly does. The methyl group and the fluoro are cis to one another, still oriented in the same general direction. And the OH group, still angled downwards from the carbon, is trans to both of those groups. So these two groups are cis to one another, and these two groups are trans to one another. The last thing you should do is then try to draw the structure with the planar cyclohexane representation. Draw the structure that would give you the most stable stereoisomer, or the isomer where all three groups could be equatorial. And so to do that, usually you have to start with a chair conformation. Well, how can we draw a chair conformation where all three groups are equatorial? Well, this one's pretty close. The only problem is that the fluorine is axial. So if we redraw a chair, we like the position of the OH group, equatorial. We like the position of the methyl group, equatorial. But we want to change this position. In changing that position, we are creating a new molecule, an isomer of this representation. So if this is axial going up, the equatorial position here would be going downward. Again, you might find it helpful to go ahead in and draw the axial positions. But certainly you don't have to. And these positions, again, are just occupied by a hydrogen. Now that we have this representation that must be the most stable representation, we can draw what it looks like in a planar structure. Again, the methyl group, since we didn't change it, oriented slightly upwards. I'm going to choose to define that as a wedge. Once I've defined that as a wedge, everything references this group. The fluorine now, instead of being cis to the methyl group as it was in this chair, notice it's angled downward from the carbon it's bonded to. The hydroxy is also angled downward from the carbon it was bonded to. And so this chair conformation would represent the most stable possibility. Now, the fluorine and the hydroxy group are cis to one another, and both of these groups would be considered trans to the methyl group. And that should give you some insight into how to draw more complicated cyclohexanes.